What's up, guys? I think I might have finally figured out the technical issues I was having before, so we're going to try this again. I got cut off kind of in the middle of this question, so I'm going to go back through it and make sure we understand what's going on. Okay, so again, we're trying to picture that there is a three-dimensional solid figure where the base of it is in this shaded region. And it says we're bounded by the function y equals radical x, so that would be this curve here at the top, this straight line x equals 4, and the x-axis. It says each cross section is a square taken perpendicular to the x-axis. So perpendicular, ooh, that's supposed to be a straight line, to the x-axis would be like this. So this would be like the base of the square, and then it would kind of like come up. This is supposed to be 3D. Oh, so talented. But it's supposed to come like up out of the screen and make a square. So this distance would be equivalent to this distance because we're being told that it is a square. So then what you're going to do first, you're going to say, okay, the first thing I need to find the area of the square. And the area of a square is just take all the sides and square them. I think before I had b squared, it doesn't matter, whatever that is. So we'll call this is the side length we're trying to measure. So in this problem, one side of the square is the distance from the x-axis up to the curve, which can be identified by just the function of the curve itself. This is almost like saying that the curve will give you the y value of the point up here, and that would be like the distance to the x-axis. And so we're going to say that s is equal to the distance where the graph hits the curve. And then to find the area of the square, we're going to square that value. And that would give us the area of each square to be x. Okay, so I'm going to go over here and I'm going to set up an integral. And the reason why I'm setting up an integral is because I basically want an infinite number of squares, and I want to add up the area of all of those. And so in order to make an infinite number of squares and also add up the area of all those squares, an integral is the function that will do that. And so an integral basically is a function that allows you to add up an unlimited number of objects. Okay, before it was just rectangles under the curve. Now we're talking three-dimensional squares. Same thing. So I'm saying add up the area of all the squares, and the area of each square is x. And so then I just need to integrate. So I would have 1/2 x squared, and I'm evaluating from 0 to 4. And that means you are going to plug in 4, and you're going to plug in 0, which is kind of silly to do because plugging in 0 still gives you 0. And then you would get 1/2 times 16, so 8 for your volume. And this is volume, volume. There you go. All right, let's look at another example. So it says find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 9. Real quick about that. In circles, circles have a format, an equation format of x minus h squared plus y minus k squared equals the radius squared. And so this value, this h value, and this k value tells where your circle is centered at. I'm just showing this real quick because this is probably going to come back at some point or another. Since we don't have an h or a k value being subtracted in our example, that means our circle is centered at the origin. So we have a circle centered at 0, 0. And then over here, the radius squared is equal to this value at the end. So that means that the radius in ours would be the square root of 9. So our radius is 3. So this is a circle with a radius of 3. And I'm just telling you that because the graphs might not be drawn for you every time, so you may have to draw that yourself. Okay, anyway, with the indicated cross sections taken perpendicular to the x-axis, and they are isosceles right triangles with the hypotenuse lying on the base of the circle. So what I like to do is just kind of go and first say They want us to draw something perpendicular to the x-axis. So I'm going to go, Lord, I cannot draw a straight line. Oh my Lord. Perpendicular. Oh my God. That's supposed to be a straight line. Perpendicular to the x-axis would be like this. Lord help me. And what they wanted is they wanted this to be an isosceles right triangle. So I'm going to go down here and draw a picture because this is just hard to see. I'm sure my picture is going to be equally as awful, but oh Lord. Okay, so an isosceles right triangle with the hypotenuse lying on the base of the circle. So this would be like the hypotenuse here. We'll call it H for hypotenuse. This is the hypotenuse of the circle. So if you go back at to look at your notes from the beginning of the lesson, I did talk about how to find area for an isosceles right triangle. But we could just start with this. Maybe the area of just any triangle is 1/2 base times height, right? Well, in our triangle, what we have is we have the distance from for the hypotenuse goes from one edge of the circle to the other. And what we're going to do is we're going to actually kind of break it into two segments. So we're going to say from the top of the circle down to the x-axis, that would be equivalent to the y value of the circle. And same thing goes for here. This would also be equal to like the y value of the circle. So the base of this triangle, let me see if I can move this out of the way. The base of this triangle would be like y value to the middle, like up here, y value to the middle, and then another y value here. So the base all together would be equal to 2y. And then in the examples I did before, I told you that the height of the triangle is always half of the base. Well, the base is 2y, therefore the height would be y. That's just a formula or pattern that would be helpful for you to remember. So we're going to plug this in and we're going to say triangles are normally 1/2 base times height. Ours would be 1/2, the base is 2y, and the height is y. Okay, let's simplify. So that would just be y squared. Now, what I'm going to do is I'm going to go ahead and set up my integral. And so what I want to do is I'm going to look and see how wide the circle is. And the circle goes from -3 to 3 on the x-axis. So I'm going to want my integral, hold on, I'm going to want my integral to do the same. So my integral is going to go from -3 to 3. And then we're inside the integral, you're telling it the area of the shape that you're being asked to find. So in this case, the area of an isosceles right triangle. And we said, we did all that work over there on the right side, and we said the area of each one was y squared. Okay, now, since we are being told to draw our triangles perpendicular to the x-axis, that means that we are treating everything with respect to the x-axis. So right here, these two arguments don't agree because one is in terms of y and the other is in terms of x. So we have to fix it. What we're going to do is we're going to look at the equation that we were given at the beginning of this problem. And the equation was x squared plus y squared equals 9. And we're going to just do a substitution to turn the y squared into something that's in terms of x. So all you have to do is solve the equation 4y squared. And you could basically say, well, y squared is equivalent to 9 minus x squared. So they can be replaced, one replaced with the other at any point in time. And so it's going to be better for us to use 9 minus x squared. That way that the argument and the variables agree. So we're going to change this. Y squared is the same as 9 minus x squared. And now we have our variables agreeing, so we can move forward. So we're going to then integrate. This is for volume. The antiderivative of 9, that would be 9x. And the antiderivative of x squared would be 1/3 x to the third, right? And then we're doing this from -3 to 3. And actually, I think I want to show you a little trick. Let me go back to my picture real quick and show you what I mean. Do you see how this circle is symmetric? Like it's evenly distributed among the x and the y axes. So what we could do is we could adjust our integral a little bit to make it easier to compute. And this only works when you have a symmetric figure. So what you could do is you could say that instead of going from -3 to 3, that you could instead go from 0 to 3 and find the area from 0 to 3, same equation and everything, but then just double it, because the area from 0 to 3 is exactly the same as the area from -3 to 0, and so you just need to find half the area and times it by 2. Now, why would you do that? Well, because when you get down here and you do this integration step, you wouldn't have to plug in, let me move this down, you wouldn't have to plug in -3 and +3. Basically, it just makes it easier for you to compute because the numbers that you're plugging in are nicer. So you would still have 9x minus 1/3 x to the third, but then you could plug in 0 and 3, which 3 is, a little challenging to plug in, but 0 is just going to be 0. So much easier mathematically. You just have to remember to double your total area if you do that. So I'm going to do it that way. So if I plug in 3, let's see, 9 times 3 minus 1/3 times 3 cubed. And then I would do that again with a 0. This whole thing would get multiplied by 2. I'm not doing a very good job with my brackets and stuff, but you get the point. Multiplying by, or plugging in 0 gives you 0 and 0, so those would just be gone. So I just need to do 9 times 3 is 27. 3 to the third is 27 times a third would be 9. And this would give me, what, 2 times 18, which is 36. So your volume would be 36.